Hello, today we are going to start our new chapter, Force System Resultants and Equilibrium of a Rigid Body. This is an overview of all subtopics we will cover. We will start with the introduction to moments, then continue moment of a force. In later sections, we analyze rigid body equilibrium. We finalize our chapter by introducing user-friendly MATLAB code. Let's start with the introduction to moments. Consider a rigid body. If the direction of the force passes through the centroid of the body, our body will undergo only linear motion. However, if direction of the force does not pass through the centroid of the body, our body will also tend to rotate. In mechanics, we call this rotational tendency as the moment of a force or simply the moment. In order to calculate magnitude of the moment, we need two factors. The first one, the magnitude of an applied force. The second one, perpendicular distance from the rotation point to line of the action of the force. We call this perpendicular distance as moment arm. Also, this should be 90 degrees in here. But in general case, moment has a vector form. It can be calculated by taking cross product of position and force vectors. Right now, I don't want to go in detail. Detailed explanations will be provided in later sections. Now concentrate moment of a force in 2D space. In 2D space, direction of the moment is out of space. In other words, moment has only one component. In this case, magnitude is sufficient to calculate moment. So this can be calculated by multiplication of magnitude of force and moment arm. Sign of the moment is important. If our force tends to rotate clockwise direction, we assign moment a negative sign. If our force tends to rotate counterclockwise direction, we assign moment a positive sign. If our more than one force applied to our system, calculating resultant moment is straightforward. We will just take algebraic sum of individual moments by considering sign convention. In some cases, finding moment arm can be difficult because we need to draw additional lines, also deal with complex geometries. Alternatively, Varignon's theorem is quite useful. In Varignon's theorem, we resolve force into the rectangular components. Then our moment arm simply becomes x and y components of the perpendicular distance. So we don't need to deal with complex geometries or additional drawings. Let's start with a simple example. In this example, the resultant moment of all forces acting on beam about point O is asked. We have three forces in here: 40 kip, 30 kip, and 20 kip. Our strategy is simple. We will compute individual moments and then take algebraic sum. Our first force is 40 kip force. Magnitude of force is already given. We need to find moment arm. To find the moment arm, we need to draw a reference line. This line is parallel to our force and pass through our rotation point, point O. After drawing reference line, we are ready to find perpendicular distance. I'm going to draw line from point O to line of the action of the force, and I obtain a triangle here, OA prime A triangle. By using trigonometric law, I can find our moment arm value. So D1 is equal to, you can see, 3 feet times sine 60. This is equal to 2.5 598 feet. We multiply this value with magnitude of force. We obtain first individual moment. This is equal to 103.92 cubic feet. The last step is sign convention. This force tends to rotate clockwise direction. That's why we assign negative sign. Our second force is 30 kip force parallel to the x-axis. That's why our reference line also parallel to the x-axis. I draw a perpendicular line from C to our reference line. This is 90 degree. I assign point as B prime, B prime, C triangle, and by using trigonometric law, second perpendicular distance is equal to 1.5 times sine 45. This is equal to 1.061 feet. We multiply this distance with magnitude of force. We obtain second moment as 31.83 cubic feet. Second force tends to rotate clockwise direction. That's why we assign positive sign. The last force is 20 kip force. We will apply similar strategy. First draw our reference line. Then draw perpendicular line from B to our reference line. This is 90 degree. I assign this point as D prime, and this distance is our moment arm D3, and this is equal to, this distance is 3 feet. 3 times this angle is 45 degree, so 6 times cosine 45, and so the last moment arm is 7.243 feet. If we multiply this distance with magnitude of moment, we obtain final individual moment 144.85 cubic feet. The last force tends to rotate clockwise rotation. That's why we assign negative sign. Now we are ready to take sum of individual moments. Let's start with first moment. M1 is equal to minus 103.92. Second moment is 31.83. The last one is minus 144.85. After take summation, we obtain resultant moment is minus 216.94 cubic feet. Here minus meaning that our resultant moment tends to rotate clockwise direction. Let's solve same question with Varigno's theorem. In Varigno's theorem, we resolve force in the rectangular components. I want to start with our first force, 40 kip force. And we can easily resolve into rectangular components. Y component is equal to 40 times sine 60. This is equal to 34.641. X component is equal to 40 times cosine 60. This is equal to 20 kip. As you see, X component passed through our rotation points. In other words, our perpendicular distance is equal to 0. This component does not generate moment. Only Y component generate moment. M1 is equal to 34.641 times our X distance is, you can see, 3 feet. That's why we multiply with 3. This is equal to 103.92 kip feet. Exactly same with previous solution. So this component, Y component, tends to rotate clockwise rotation. That's why we assign negative sign. Second force, 30 kip force, parallel to x-axis. In other words, only have x component. We don't need to resolve into components. Also, our moment arm has only one component, y component. We previously find this distance. This is equal to 1.061 feet. We multiply both terms and obtain our second individual moment. 61 is equal to 31.83 kip feet. This force also tends to rotate counterclockwise direction. That's why we assign positive. That's why this should be positive value. Exactly same with previous solution. The last force is 20 kip force. We need to resolve into rectangular components, and from geometry this is a x component, this is our y components. This angle 45, also this angle is 45 degree. So x component is equal to 20 times cosine 45 degree. This is equal to 14.142 kip. Similarly, y component has a same value because we have 45 degree. 14.142 kip. Also, this is our y component. Let's compute moment R components. This is our y components. You remember we previously calculate this value. This is equal to 1.061. From geometry, this is 2 times of this value. That's why this is equal to 2.122 feet. Similarly, this length is also same value. That's why in total x component of moment arm is equal to 6 plus 2.122. This is equal to 8.122 feet. Now we can compute the individual moment. Let's start with the x component. M3 is equal to 14.142 times 2.122. This force tends to rotate clockwise direction. That's why I put negative sign in front of computation. And then I want to continue with the y component. 14.142 times 8.122. You can see y component also tends to rotate clockwise rotation. That's why we assign negative sign. After calculation of this value, we will obtain same result with previous solution. This is equal to minus 144.85 cube feet. As you see, all individual moment values exactly same with previous solution. That's why our resultant moment will not change. This is equal to minus 216.94 cube feet. This is the end of our video. Thanks for watching.